Okay, so let's see. Committee is all here. Okay, welcome everyone to Jeremy Ritter's dissertation defense. It's been a great pleasure to work with Jeremy for a number of years now. Jeremy has written some highly impactful papers that are recognized in the field. He'll tell us about his work today. He's also set a new standard for me for his tenacity and perseverance with the most difficult simulations imaginable. A standard that I doubt anybody will beat from now on. I'm just going to finish here and then pass the stage to Jeremy.
Thank you, Milos. So as you said, my name's Jeremy Ritter, and this is my dissertation talk. So over the last 6 or so years, I've been involved in a number of projects, mostly numerical simulations, involved in studying the role of the first stars in shaping the early universe, specifically the supernovae by the first stars. So observers are constantly pushing back the veil on the unseen distant past towards the high redshift early universe. Theorists can tell us something about how the universe started under the Big Bang Theory. My simulations will bridge the gap between observations and theory. So let's start with some observations, right? What are we looking for? So here we see carbon over iron ratio as a function of the iron abundance, and we call the iron abundance metallicity sometimes, which is just a proxy for how much heavy elements have been included. And as we see, as we go down in metallicity, you get more carbon relative to iron, and the scatter increases. There's even a few extreme stars that don't even fall on this nice, neat picture. In particular, this star up here, Keller star, has basically no detectable iron in it at all. And so that could in principle be way off the chart there. As metallicity increases, these abundances converge and the scatter decreases towards the solar value here where the yellow star is at 0 and 0. Metallicity sort of gives us a cosmic clock that allows us to look back in time and tell something about the cosmic evolution history as enrichment occurs periodically through time. So how can we link the measured abundances of these metal poor stars back to potential first star progenitors that could have enriched them? What are the details of mapping from one generation to the next, and in particular from the first generation of stars? So as you enrich multiple times, some of these signatures from these very high variations get washed out, and that's why we average towards the solar values. So it's long been theorized that the metal poor stars could tell us something about the very first stages of chemical enrichment, how the first stars dispersed their metals and were recycled back into a new generation of stars. So that's what I'm going to talk about here in the first half of the talk. So starting in the Big Bang, which you guys can't see, it's off the top there, the universe was created with basically hydrogen, helium, a little bit of lithium, but basically nothing else. No heavy elements that we're used to today that you and I are made out of. The first stars that emerged out of the dark ages also didn't have any heavy elements. They were just hydrogen, helium. So those stars had to create their own heavy elements, and we know that stars power their cells through their lifetimes by fusing light elements into heavy elements. The most massive stars, when they exhaust all their fuel, they explode as supernovae, and they distribute these heavy elements that they've synthesized out back into the surrounding medium. They only live a few million years, up to maybe 10 million years or so, before they start exploding and enriching the early universe with these heavy elements. So how did the first supernova jumpstart cosmic chemical evolution? That's a big question. So here we have a periodic table which shows that we can see the signatures of heavy elements coming from all sorts of different sources. At the Big Bang gave us hydrogen and helium up here at the top. Massive stars can be shown here in the green. They give us all these nice light elements, carbon, oxygen, the alpha elements that build up towards the iron right here, and also the iron group elements. On longer time scales, we have low mass stars, which live quite a bit longer, but as they're dying, their outer layers can be shed and they can give back some of those heavy elements in the surrounding medium. And also white dwarfs on similar long time scales. These smaller supernovae, of smaller, older stars will explode, and they provide a lot of the iron group elements. Oops. Particular note the different sources of carbon and iron. We've got massive stars contributing both, but low mass stars contribute carbon but not a lot of iron, or none. And then white dwarfs contribute a lot of iron but not a lot of carbon. So thinking back to the plot we saw earlier, can we tell something about the different origins of different elements and the abundance variations that are caused by enrichment from different sources? Rounding out the periodic table, neutron stars and neutron stars and cosmic rays produce a few elements in small quantities. All right, so we mentioned that all the massive core collapse type supernovae produce alpha elements, and we can see that in this plot up on top, where we've plotted, we see a plot of magnesium enrichment versus iron as a function of metallicity from Sneed and Cowan and Galeno. And we can see that core collapse supernovae generally enhance with alpha elements, enriched with alpha elements across the spectrum. But for the same stars, we see a huge scatter in other types of elements, for instance, the R process elements. And what does this mean? Perhaps only a small fraction of the massive stars contribute these sorts of elements. So we have alpha elements coming from all of them, but there might be some sensitive mass, rotation, or multiplicity that causes other effects to happen for different elements. So what are the conditions that cause these sort of variations to come about and to survive? And in particular, we note that the chemical abundances that we see in the stars might not actually converge to the overall yields from the supernovae that enrich them. Here we show some of the nearby faint dwarf galaxies. So these are actually galaxies versus just stars in the Milky Way that we showed before. These galaxies are very faint, and they have very low average metallicities that decrease as they get fainter and also less massive. The metallicity spread, so the difference between the maximum and the minimum metallicity increases as well as you go down in mass. And it's pretty significant at the very faint end, right? So this could be due to them forming out of the merger between some chemically distinct progenitors that then get some small metallicity and some large metallicity that merges together, creates a big spread. Or you could have some sort of inhomogeneous local enrichment. You've got supernovae that enrich part of the galaxy a little bit more than this other part. Maybe a different supernova later enriches the other part differently. As well, we see metallicity scales with the luminosity and also the mass. So this sets up a sort of mass-metallicity relationship. But can the metallicity still be an accurate cosmic clock when we go all the way to the smallest metallicities? Because of this scatter, we think that it might muddle our ability to use this as a cosmic clock at the very, very lowest metallicities. So now we plot the same ultra-faint dwarfs, but actually looking at abundances. So here we've got alpha abundances. This is an average over several alpha elements, including magnesium, carbon, silicon, I think. And we can see that they generally all show alpha enhancement, especially at the very lowest metallicities. As you go higher in metallicity, you see this alpha enhancement decline towards the solar value. And pretty much all of the examples except for here in Segway, which is pretty alpha enhanced at all the metallicities. So this process of homogenization can happen very quickly. where we've got the abundance variations washed out as more sources contribute. And here when we plot all of them together, we see this relationship. We sort of can kind of maybe see a line right there that shows this trend of decreasing abundance variations. Although we think this is a signature of type 1a enrichment. So after a while, you've got lots of alpha elements that were provided by massive stars. You wait for a while, the type 1a supernova can go off. The white dwarfs provide iron that brings this back down to the solar values. So we kind of see a schematic cartoon diagram of that here. If you just have massive stars, it gets you up to this line. That's sort of the one-shot enrichment scenario. If you very quickly start forming low-mass stars and have white dwarf explosions, then you can bring yourself down to the solar values very quickly. Or if it takes a long time, maybe you come down over here. And Volker and Anna Frebel made us this nice plot where they've put some of the actual measurements on here, and you can see that we do follow this relation pretty loosely. You've got lots of stuff along here on the core collapse enrichment track, and then they sort of fall off along the 1A enrichment track until they get to the solar values. So what kind of questions can we ask about this? How can the observed abundances be linked back to the yields of the first supernova? That was the original question that we wanted to answer. Can the metal-enriched stars that form after these supernovae, can they form promptly before other sources have contributed? That's another question. Does the hydrodynamics of supernova ejecta homogenize the abundances, or does the explosion introduce some additional anisotropy that we have to account for? And finally, what are the general properties of the IGM, ISM, and metal-enriched stars when the first galaxies begin to assemble? So here we can see a simulation done by Chalent Safranik-Schrader, who was here not too long ago. It's actually possible to simulate the formation of the first galaxies from cosmological initial conditions. We take a box, we seed it with density perturbations from the cosmological background, and we let it go, and we form these little mini halos. And then we zoom in on the mini halos to smaller scales. We resolve individual clouds, and actually we can see something about the star-forming cloud here where POP3 protostars are forming. Now these stars are metal-free, and that means that they can't cool very efficiently. So it's typically thought that they're a little bit more massive than the stars that we form now with lots of metals. But those masses were originally thought to be extreme, like 100 solar masses or more. And further simulations have continually driven down that mass scale to where we now think they're a few tens of solar masses. Much more in line with stars that we know about. They don't have to invoke any sort of extreme explosion scenarios like pair instability. We can just assume that they're typical massive star supernovae. So these sorts of simulations allow us to study the POP3 star forming process and tell us something about the characteristic mass scale. So we can use these, I can use these, to then build up the cosmological environment. And in our simulations we use the Flash adaptive mesh hydro code. And we've inserted into that dark matter and gravity, as well as heating and cooling in non-equilibrium and in equilibrium regimes. We insert a star particle in this mini halo. We allow that star particle to photoionize the gas, heat it up, and then when the star's lifetime is over, we zoom in to even higher resolution and we insert a supernova remnant. We do this in the free expansion phase with kinetic energy before the remnant has actually interacted in a significant way with the surrounding medium. And then we evolve it for many tens of millions of years as the ejecta is dispersed and then recycled and recollapsed into a new high-density cloud. So here we can see a little schematic of the photoheated gas. As you heat the gas in the center, it expands, it gets overpressure and expands like a champagne flow. And the density in the interior increases, and you get a nice thick shell out there at the head of the champagne flow. So this provides less resistance to the shock wave that's going to go off inside there. So here we see a supernova exploded inside of a mini halo. This is 8 million years afterwards. We see density, temperature, and metallicity on the right. We can already see after 8 million years these filaments from the cosmic web have already started to penetrate back into the center, delivering cold primordial gas back into the halo. The metals are distributed sort of perpendicularly away, and they avoid the filaments and enrich the voids up perpendicularly. So let's look at the central bit and say something about the gas that's falling back in. The baryons, the normal unenriched gas, starts falling back in about 1 million years after the explosion, where the metals begin to have a net inflow after a few million years, maybe 2 or 3, 4. The metallicity of the inflow is actually pretty large on a coarse grain average, but when we look into the interior, we can see that it's actually very inhomogeneous. It's not mixed at all. Right? Here we see density slices with ejecta particles, tracer particles in projection. And we can see those particles are distributed all over the place. And even as they stream back in here, they're streaming in sheets that don't really mix until they get into the very center and start to swirl. So after 40 million years, the ejecta is still highly inhomogeneous. Unfortunately, in this simulation, we don't actually zoom in on that little cloud there and really see what's going on inside of it. So we just have to assume, it's coarse-grained, and we'll have to find out what's going on in there later. So let's run some more simulations, right? Let's do a better job. Well, the next thing we want to try is we had one supernova in a mini halo. Well, what if there's more, right? So simulations of POP3 star formation have also shown us that these clouds that would form a large massive star can sometimes fragment due to cooling or rotation or other factors. And those fragments will, instead of forming one large star, will form a few lower mass stars. And these low mass stars will have a range of different masses, and they could have, in principle, different properties. The supernovae could have different yields, depending on mass or other details. And as well, the temporal separation, the cadence of explosions could also introduce additional variability into the enrichment. So how do we think about all these kinds of additional complexities? Well, we make a simulation, right? We just see what happens. So we have the same mini halo as before. We allow it to be heated by now a much larger cluster of stars, which more radiation, so it makes a nice smooth H2 region in the mini halo. Then we insert supernova remnants. We zoom in again to high resolution and insert them in the free expansion phase. Multiple supernova remnants will eventually overlap and create a big super bubble, and the super bubble will blast its way out of the mini halo. We also individually tag the tracer particles that we showed before. We've marked each individual tracer particle so that we can track it from the enriched cloud that collapses at the end back to the original source, either the supernova that it came from or what location, whether interior or exterior of that supernova. All right, so everybody's been waiting for movies. Here we go. Here's a movie. Here's the mini halo showing the virial radius here. It's about 150 parsecs, I believe. First thing you'll notice is the photo heating as the mini halo puffs up, and then the supernova is inserted. So it transfers its energy into the surrounding medium, kind of dies out, but then the next one goes off and reinvigorates it. And now the third one comes up, and we've got ourselves a super bubble. You can already see that it's interacting with another bit of filament that's actually out of the plane of this slice, and ablating some of that cold gas and mixing with it. After a couple million years, we'll see the cosmic web filament penetrate from this side as well. So after this last supernova, we'll zoom out, and we'll follow the ejecta as it is dispersed. So I already noticed that the shell here is starting to break up and fragment Those fragments are just sort of coasting out. And now the filaments are starting to recollapse and incorporate some of those metals. And then we'll speed up and follow that. And now this cloud collapses to high density after 200 million years. So that's a much longer time scale than the other simulation. But we added a lot more energy into this mini halo. Yep.
Can you say what the mass it has?
So it started with
200?
10 to the 6, and after 200 it was a few times 10 to the 7, I think. And we can see that the real radius has grown from about 150 to 300 or so. So here's the same movie, but now we're showing the metallicity times the density. So we're just highlighting the metal-enriched portions. And I'll let it play. So there we see the center is very highly metal-enriched, but then the outside has no metals yet. And you also notice that the shell doesn't really get metals incorporated into it until it gets thin. So as the metals are incorporated into the shell, they allow it to cool and become thin. And we see the primordial gas being ablated off of that filament as the blast wave passes it. Also on this side we can see that the metals are actually being just deposited on the surface of that filament. They're not actually being mixed yet. It's not actually until the filament falls back into the center and then you get rotation that things start to actually mix together, at least on the scales that we resolve. And then as we speed up, it will swirl in, and there we go, we got infall. Cool. As we can see when we zoom into the central few hundred parsecs, the ejecta is still highly inhomogeneous, right? These tracer particles are still very sheet-like as they fall in. Here we plot the vorticity magnitude, which essentially gives us a measure of the amount of rotation in the gas. The higher the vorticity, implies a shorter mixing time. And we can see out here there's very low vorticity, and it's not until we get to the very center where we start actually zooming in and resolve smaller scales that we can see the vorticity ramps up high enough that we can assume that mixing is occurring on smaller scales, but only there in the center. What can we tell about the cloud in the center? What are some of the statistics that we can measure from it? So after 200 million years, when it recollapses, we follow it until it gets to a density of about 10 to the 4. The average metallicity here is actually pretty low because it's been diluted with a lot of cosmological inflow because it took such a long time to recover. When we actually look at the contributions from each supernovae, we see that they're sort of in order. The first supernova contributes a little bit more than the second one, a little bit more than the third one, and a lot more than the last two supernovae, right? So what could this be due to? We saw the supernovae as they enveloped that filament, they sort of just superficially deposited the metals on the outside. Whereas the last few supernovae didn't have another supernova come by and condense the rest of it on there. So it stays at high entropy, stays hot, and doesn't get incorporated when that cosmological infall starts to swirl and recycle gas. So the mixing of ejecta and primordial gas is delayed until this fallback happens and the collapse to high density occurs. So the one thing that we can learn from this is that metal enrichment seems to be biased to the first supernovae, right? We've also plotted this for a single supernova. This was a project done with Alan Sluter and I, where we see a similar outcome, but here instead of different supernovae, we've plotted the different shells, different mass shells. So the first shell is the innermost shell, second shell is above that, and then the seventh shell is on the exterior. And what we see from this is basically the same thing where the high entropy stuff, which in this case was in the interior, doesn't get incorporated as preferentially as the material that's on the outside that gets compressed onto the cloud. Well, this is a really very busy plot, and I don't want you guys to really worry about it too much, so I'm just going to summarize. This basically shows the relative mixing between the different layers, either layers in a single supernova or different supernovae in a cluster. And the red is just the central 50 parsecs of the cluster. And the very narrow spikes show that there's a very small range in relative densities. So that implies that the material is fairly well mixed, at least in that central 50 parsecs. Now, if you consider the green lines, that's all of the ejecta globally. And you can see the first couple of layers on the single supernova have a very wide distribution. So they're not very well mixed with any of the other layers. As well, the last supernova here is also not very well mixed globally with the other supernova. And that trend of mixing increases towards the earlier supernova and towards the outer layers. What are some other possible sources of bias? Here we show a couple of high-resolution simulations very early in supernova explosions from Wong Rathonarat and Sean Couch, who is also here at one point. This one's very early, only a few hundred seconds, and this one's maybe a little bit later, a few thousand seconds. And what we see here is a spherical carbon shell, a bunch of little oxygen fingers, which are more or less isotropically distributed, but still have some variability going on. And then we have these big giant plumes of nickel, which will eventually decay to form iron. And these guys, you know, if they shoot out this direction and hit a cloud, then you'll get iron. If they shoot the clouds over here, then you don't get any iron, right? And here on the right, we see what we call stratification. We see a shell of silicon, which is one of the alpha elements, and a core of iron. And they're differentiated, right, like an onion shell. So how could these things be included in our model? So let's take a break from simulations for just a second and make a little toy mathematical model. So here we have a y vector, which is the yields that supernova theorists calculate these yields, and they tell us, okay, a 60 solar mass star should produce this output. We run a simulation where we explode a supernova, follow the hydrodynamics, and see what recollapses. And so by multiplying this y vector into our transport matrix, we can map from the input abundance yields to the output measured abundances that we might be able to see in the first metal-enriched stars. The problem here is that T is not the only answer, right? There could be, in principle, multiple T's. We've done one particular explosion. You could also include other effects, such as stratification and anisotropy, and how do those effects play into it? So if we just consider that the transport and everything is completely well mixed beforehand, then we would get here to this blue spot, right? That maps whatever our input abundances were, which in this particular case I think were just solar, to this low metallicity abundance here. Now that's just the transport, that's just the hydrodynamics of supernova and dispersing and fallback. So what if we include some sort of different explosion models? Instead of maybe being fully mixed, the ejecta was stratified, where we have iron in the core and carbon on the outside. Well, that would pull us up here. If we consider what we just learned in the previous simulation, the inner layers don't get as much representation in the recollapsed cloud, so we would get less of the iron, and that would move us up here. We get more carbon relative to iron. But we still have basically the same amount of carbon, and the carbon scales sort of this direction. Now if we include anisotropy, if one of those plumes just happens to hit a cloud that gets enriched, it'll fall down here. And if one of those plumes just happens to go, you know, further out, it'll fall up here. So we can get a wide range in variability all along here. And what do? Right? We got to keep making more of these models. In particular, how can we explain the Keller star that's way up here on this plot, right? Is it possible that this star had a single progenitor? Let's test that hypothesis. We'll do another simulation of another supernova. So first we form a mini halo, We'll zoom in on it. We'll heat it up, blast it apart, put a supernova in there, and then we'll follow this gas, and we'll zoom in at high resolution as the gas recollapses. So here we also have the tracer particles, and they're tagged so we can tell what's going on inside as well. And then after only 13 million years, this guy is recollapsed. All right, here we're showing basically the threshold for collapse. We've plotted entropy, or rather an entropy parameter, as a function of metallicity. And this entropy parameter depends on the temperature and the density. So in order for gas to collapse, it needs to have high density and also low temperature. Right? It's got to be able to cool in order to collapse further. Over here on the left, we've got cold gas that's pretty dense already. So as you go down in this plot, the temperature decreases, and as you go sort of down and to the right, the density increases. So over here we've got fairly high density and fairly cold, but it's not metal enriched. And not being metal enriched, it can't really cool very much further without some help. Over here we've got very metal rich stuff, but it's super duper hot, and it's also not very dense yet. So how do we get this stuff and this stuff to collapse? Well, here in the middle, they will eventually mix together to some degree and loiter around in this phase until they cross a threshold. The threshold allows them to collapse in sort of a runaway fashion. We just happened to recover this critical metallicity here, which is thought to be required for low mass POP2 stars. So that was sort of just a nice surprise. So the metallicity in the collapsing gas, we can see, is it doesn't have a large spread when it starts to collapse, but the average is preserved when it collapses. But now the spread decreases. So as it's collapsing to higher and higher density, more turbulence is going on inside there, and we average out whatever variations were present. So let's see if we can model the enrichment bias using this new information. We have a new T from this new simulation. Now let's see if we can include the effects of all these different models, right? We've got transport, we've got stratification, we've got anisotropy. What can that tell us? Well, the model here can, in principle, map to any one of these positions inside this square, right? So just like your luggage at the airport, this TSA enrichment model can send your yields to some random location and you'll never find them. So we got a cartoon here that illustrates the idea that we need to throw out the old paradigm where a supernova sort of expands in a sphere, enriches a spherical region uniformly, and the stars that form out of that will then all have the same abundances. And now the new model that we want to consider instead is that a supernova explodes, the enrichment is very inhomogeneous, and the stars that form out of that could have some irreducible scatter in their abundance variations. All right, some conclusions from all this. The first metal-enriched stars likely formed before the other nucleosynthetic sources had time to contribute and homogenize the cosmic abundances. So that's good. Hydrodynamic biases must be taken into account when we're trying to reverse engineer the character of the contribution from the first supernovae. Specifically, the measured abundances in the ancient metal poor stars might not reflect the cumulative output yields from the first supernovae. There could be some additional yields that are hiding somewhere out in the circumgalactic medium somewhere. We require many more data points to complete the statistical picture. We've run, three data points, so we need a lot more. Okay, now for something a little bit different. When the wind blows. We've got a picture of M82 here. We can see a very, very strong outflow coming perpendicular to this disk. M82 is one of the most well-studied galactic outflows. We've got gas that's moving at 1,000 kilometers, several hundred kilometers in the warm stuff, streaming out of this very high star formation rate galaxy. Well, these winds are, or these outflows rather, are important across a wide range of mass scales, from Milky Way scales all the way down to the very smallest galaxies. Here we see silicon emission from Doppler shifted gas in the outflow that traces the outflow. It's been Doppler shifted relative to the central starburst at the center of the galaxy. These outflows help to regulate the gas reservoir that's available to form new stars. So they push gas out. When stars form in the center, they heat it up, they inject energy, and that pushes gas out, and it stops more stars from forming if it's self-regulated. So we believe that high star formation rates lead to high outflow rates, right? Which we see here in these plots. A plot as a function of the star formation rate. As you go to high rates, you get strong outflows. At the low end, you sort of see that it turns over and caps out, and maybe there's some floor there. So here we plot the star formation rate as a function of relative to the average star formation rate that we expect for a galaxy of that size on the main sequence. So we see, again, that strong outflows are expected when the star formation rate is above average, but that weak outflows on the left might actually be representative of self-regulated mode of star formation, where a gas is sort of collapses, forms new stars, energy is injected, keeps more gas from falling in until later. Whew, we got some galaxies, right? The ultra-faint dwarf galaxies. Could they be examples of the first galaxies? They are the lowest mass dark matter dominated things we know. Here we've got Segway again at the very bottom of that. It's one of the faintest. They're very chemically primitive that we saw earlier. They have these alpha enhanced abundance variations, and they're very metal poor with a lot of scatter. They have very large mass to light ratios, so they're very highly dark matter dominated. What does this mean? We expect the mass to light ratio just from cosmological infall to be of order 5 or 10, but when we measure it, it's actually more like 1,000. So that means that whatever gas was supposed to be there has been removed, right? Only a few percent is left in stars, so all the rest of the gas must have been removed. Was it removed by the Milky Way as they're orbiting around and had it stripped? Or was this gas blown away by radiation and supernova explosions before, a long time before? So these ultra-faint dwarfs, they're very low mass, which is implied by their ability to survive in the Milky Way's halo. If they were much larger, they would have been tidally disrupted and merged into the halo. So this suggests that the ultra-faint dwarf progenitors formed in primordial halos with masses of order 10 to the 6, 10 to the 9, which is in the familiar mass scale that we've been working with. So this is great because these are amenable to direct numerical simulation. So we can actually form one of these galaxies at this scale and put some stars in and see what happens. So that's what we do. So here's my final project. It's about supernova-driven outflows from the first galaxy, where we've taken a small disk galaxy comparable to a first galaxy, where we've cut it out from a cosmological simulation done by Andreas Pollock when he was here. This is a billion solar mass halo with a radius of about 3 kiloparsecs at redshift 10. So the first thing we'll do is we'll insert a cluster. We'll allow that cluster to photoheat and ionize the disk, puff it up. Then we'll zoom in and insert a succession of discrete supernova remnants, allow them to overlap and form a superbubble. And then we'll follow that superbubble as it tunnels its way out of the disk and hopefully develops a wind or an outflow. So here's some properties for this disk. It's about 10 million solar masses of gas confined in this 250 parsec region. The thickness there is about 65 parsecs initially, and the density is average about 10 to the 3. So here we see it in the face-on view and an edge-on view before the photo heating has been started, and we're going to run the movie, and we see heating in the center causes the gas to flow out, and as it flows out, it piles up and creates a little shell. And as well, the scale height now has been puffed up to about 3 times its original thickness. The density in the center has been decreased as well roughly by a factor of about 100. So this should make it a lot easier for the supernovae to expand inside there. Yes, sir?
Could you say just briefly how you did the radiative transfer of the ionizing radiation?
So in this one, we just did really simple. The flux is, let's see, the flux was Q, which is our number of photons per second, divided by 4 pi r squared. And we just assumed that it's optically thin, which we calculated was a decent approximation after the very initial gas expands just a little bit. Then this holds pretty well. So we assume that the stars will eat their way out to that point and then get the rest of the way out. All right, so here we see the density projection zoomed out a bit. We show the real radius here at 3 kiloparsecs, and you can see the puffed up disk there with all these little subhalos floating around it. Now we'll zoom into the central 100 parsecs. Oh, and it's all red. We can't see anything. So let's take a slice through the middle. All right, now we have a slice, and we can play this movie. All right, the center is marked with an X, and the supernova explosions are not necessarily going to emanate from that X. They're being inserted randomly near that center. So we can see already after the third supernova that a bubble has formed. And inside of the bubble is hot. And then outside the bubble has a shell, and the shell is cooled down. There's a lot of these supernovae. They just keep coming.
Now, are they forming because some criteria is satisfied in the gas dynamics?
No,
A new supernova?
so we insert an instantaneously formed cluster. We just assume the whole cluster forms at once, and then we've got some 1,000 stars or whatever, and we just start firing them off one at a time. So we actually took the cadence from like a Starburst 99 simulation and got the ordering down. All right, so here we are 2 million years after the first explosion. The shell here has just barely gotten to about 90 parsecs away, which is just right at the edge of the disk. And if we zoom out, we can sort of get some context here. In the slice plane, the disk is sort of at an angle here. But we can see the edge of the bubble is just about to break through and get into that lower density stuff. And once it does that, we expect that's when it's going to fragment. It'll accelerate a little bit, fragment, and break up. And then hopefully the hot wind will be able to leak out through those fragments. All right, so let's plot the maximum radius of that superbubble over time. Initially, it starts out as a single supernova where we plot the Sedov-Taylor solution that scales, the radius scales as t to the 2/5. It sweeps up a shell of gas. That shell is able to cool, and then the remnant slows down to this t to the 2/7 solution for the snowplow. If you now have more supernovae going off, and here the average time for between supernovae is 66,000 years, so we'll see the second supernova goes off right here, and the third one at that red line, fourth, fifth, sixth, so on. After the third supernova, which is the first one to explode inside the bubble from a previous supernova, we see that this reinvigorates the bubble, and it jumps up here to this continuous snowplow solution, which scales as t to the 3/5 because energy is now being continuously input into the center. But this only happens that we recover this solution after several times of the supernova delay time. So we need multiple supernovae to make that happen. This plot is a phase plot of the radial velocity and radius. So we see the hot metal-enriched bubble. The stuff inside the bubble is there, and it's trapped behind this shell. And the shell has a temperature gradient where the supernova remnants are colliding into the back of it, and the front of the shell has been cooled down to basically 10,000 degrees like the rest of the ISM. And there's a huge extreme temperature gradient through that shell. And so we see that's confining the hot, low density, high metal enriched stuff in the center and separating it from this cold ISM out here. Now, if we consider that the shell is expanding outward, but it's also slowing down in time, where do we think that might end up? well, it's slowing down as r to the minus 2/3, so we can just project that forward along these streamlines, and it looks like the cold shell here is going to end up being deposited somewhere between the scale height of the disk and a few times the scale height of the disk. So it's not actually going to, those cold dense clouds are not actually going to get out. They're going to be dropped off somewhere in the outer halo. And it'll be this hot fluid that leaks through behind them that creates the wind. Now this wind is going to depend on how much mass is loaded into it from those clouds, how much energy is radiated away by transferring it into these clouds, and also how much metal is being deposited in these as well. So look, there are some conclusions we can draw from this simulation. Well, the shell fragments are likely to be deposited outside of the disk, but they probably won't escape the galaxy. So they're going to be embedded in the outflow, and perhaps they'll mix, and we can see if the hot wind can channel through this cavity and break out around them. So we hope the wind will stream through these fragments and ablate some of the gas off of them, mix with it, and create a warm phase. And it's actually that warm metal-enriched phase that we can see with metal ion emission. So measurements of the metal energy and mass loading, we hope, can be linked to wind theories and also inform observers about what to expect at high redshift. One final piece of information that I didn't really touch on, but that is also very important, is the resonant scattering of Lyman alpha through these outflows and off the walls of these outflows and the clumps in these outflows can actually boost the escape fraction of ionizing radiation, which has implications on the reionization of the universe at early times. Okay, so understanding outflows, or understanding the source behind outflows, is particularly key for understanding chemical evolution and reionization in the early universe. In the future, we will have a great wealth of new data coming in from these 30-meter class telescopes, like the Giant Magellan Telescope, the 30-meter telescope, or the European ELT. They will give us a bunch of new data, particularly spectroscopic data across a wide range of sources. Potentially, surviving fossil relics of these first galaxies might actually be sitting around nearby if they're analogous to these ultra-faint dwarfs. And we can actually go look at them right now, doing something we call near-field cosmology. And soon, hopefully, for the first time ever, we'll be actually to directly observe the first galaxies when JWST comes online, where it launches in a few years and comes online a little bit after that. So that's very exciting for the prospect of actually looking and seeing these things. So it's now customary that I explain a little bit about what I'm going to do next, since I'm done with my science talk. I'm very interested in artificial intelligence and other forms of data science and data engineering, but mostly I'm just going to finally be able to mow the lawn that I haven't done. It's about that tall. All right, I'm done. Any questions? I'll take them now. Yes.
I mean, we have plenty of time for questions. 10 minutes at least.
Yeah.
Early on, you reflected on the shift that had taken place in the paradigm of what the first stellar masses were.
Mm-hmm.
And earlier on, they were sort of 100 solar mass or above. And then for a while, it seemed as if fragmentation might actually allow full range to solar mass.
Mm-hmm.
But I heard a talk recently, and then there was also an issue of radiative feedback that would limit the mass. But I heard a talk by Thomas Greif, who was here at one point, just in Strasbourg at the reionization meeting in June, where his conclusion was that the current status of trying to overcome the limitations of sync particles that are inevitable in some of the simulations of that fragmentation process, which can't be reversed by merging. That the current understanding is that we're back to being able to assume the stars are typically 100 solar masses. And that surprised me, but that's in his concluding slide.
Yeah.
I wonder if,
That surprises me too. I mean, that's certainly not out of the realm of possibilities. And I think we simulated sort of the more massive end of the moderate masses. So we didn't go all the way down to 10 solar masses or solar mass. We sort of kept it in the range of 20 to 80-ish.
I mean, it still doesn't,
Yeah.
it doesn't push it necessarily up into the parent.
Right.
That's higher.
Right.
But-
So the actual masses of the ejecta in our simulations don't really affect the results too terribly much. They can increase the metallicity, but all the supernova remnants are being inserted with basically the same energy. So the hydrodynamic effects are pretty similar. So we could definitely simulate a bunch of these higher mass stars. I don't think it would change the conclusions very much. If we use the same energy, unless we go to this pair instability regime where they now have a lot more energy and they take a lot longer time scale to recycle. And of course they'll have different abundance patterns. Yeah, Aaron?
Yeah, so in one of your later phase diagrams, you're sort of missing this cold phase. All the gases above 10 to the 4 Kelvin.
Which one was that?
Yeah.
Oh, that's the wrong one.
I think the radial.
Oh, the last one?
Yeah. So is that just an effect like it's there but it's hidden, or?
What are you talking about? You talking about over here?
Yeah, all the blue, it pretty much.
So the blue is just the cold gas in the ISM of the galaxy. And I didn't tell you guys what these lines are. So this is the virial radius here. That's the edge of the galaxy essentially. And here is the escape velocity.
Yeah, so I mean, this is warm. Like cold would be.
Oh yeah. So I say cold relative to the supernova ejecta. This has actually been ionized by the star cluster. So it's warm ionized medium. Yeah.
Yeah. So, but eventually that like the cold clumpy phase will self-consistently begin to form.
Right.
But are you?
So we get a little bit of that in the shell. So the shell that's swept up by the H2 region, that can stay pretty cold because it's pretty dense still. And then also the supernova shell has a little bit of actually cold gas. But it's not a lot. It's only the very densest stuff that is able to be cool. Everything around it is still pretty warm. Yeah.
Did you find any circumstance in which the gas that was driven out returned in a kind of galactic fountain?
So in this simulation, we're just showing preliminary results. We're actually still running it. It's still going right now. We've just got it to where the bubble has reached the edge of the disk. So we haven't actually broken out yet. We expect it to continue and break out just based on the evolution over time. So we're going to keep running it, and in the next 1 million or 2 million years of simulation time, we should see the outflow actually start to leak through. Now, we would probably have to run it for a much longer time scale, 100 million years, in order to see some of that fallback return. But we might start to do that after we've developed an outflow. We don't have to do so much machinery on the center, with the supernova remnants being inserted. Yeah, Keith?
Does the amount of gas, do your simulations allow you to be able to say anything about the amount of gas metallicity mixing as a function of the radius as you go out in the galaxy?
We haven't actually calculated that, but in principle, yes, we can. So we have tracer particles that we use, and we can estimate the local metallicity from the tracer particles, just the abundance of tracer particles themselves. And we've done that in my first paper, and I didn't show it here in the talk because it's very difficult to understand the plots and stuff. But yes, in principle, we could do that, though we didn't resolve very well in that first simulation enough to be able to say anything about the mixing other than just coarse grain mixing.
That's a way to link it to the observation.
Right. It's to be able to see the inhomogeneity in the outflows and stuff like that.
So you can essentially measure the dispersion of the abundances as a function of R, and then compare it to the simulations.
Oh yeah.
Try to figure out an estimate of the mixing.
Right, and then oh, that's a good idea. We'll have to try that. Any other questions? All right, well, thank you guys for coming. Hope you enjoyed it.